Welcome back. So now this chapter is we're is all about atoms and elements and what do the subatomic particles uh, make up our make up everything that we experience. So without further ado, we'll start looking at chapter 2. Now, before we get started, we define what is an atom. Atom is the smallest particle of an element that can be itself identified as that of an element. Uh, or the first known usage of the word atom was by Democritus and his predecessor, with the word atomos meaning indivisible or indivisible particles. The idea that a particle that could not be split up any further. So we'll start off by looking at use an analogy with paper clips to understand the difference between an element and an atom. I'd like to start this chapter with an analogy about atoms and elements. So for this analogy, we're going to pretend this pile of paper clips are the element gold. So we have a big pile. If all these paper clips were gold, I, I wouldn't say no to those. That'd be a decent amount of gold. But the idea for element, it doesn't really matter how much of it you have for it to be an element. If I take this pile, cut it in half. So I cut my big old block of gold, split it in half. I've lost some of my gold. But this pile, all of these paper clips, still gold. I can keep splitting it. Remove some of my gold. Maybe it's down to a simple bar. Cut it in again. Maybe it's down to some pebbles. I split it again. Maybe it's down to some fine gold powder, and I keep splitting. Now, the idea is that at some point, we're going to get to a point where there is but a single atom of gold, just one piece of gold. And we cannot go any further. If I were to split it even further, it would cease to be gold. It would be down to its subatomic particles. But an atom is the smallest unit that we can have that's still considered to be an element. When we split the atom, we're actually going to, as we find out later, produce a lot of energy. When we split the atom, we're essentially doing nuclear chemistry. This could be nuclear fission. What happens in a nuclear reactor, as we'll see later, is that we bombard an atom with neutrons, causing it to fission into several different other elements, releasing a lot of energy. Now, if we have this occur rapidly enough, we have our nuclear explosion. If it's slow and contained, we can actually just use that as our nuclear power. But we'll talk about that more a little bit later. Now, of course, not all atoms look the same. Some of them are smaller. Some of them, as we see, are bigger. Big atoms and small atoms. We can combine them together. We could bond these two guys together, make a bond, a paper clip, big paper clip and small paper clip. But that is not till chapter 3. Looking at the size of an atom, the average size is incredibly small. Just looking at gold alone, gold, something like one gold atom has a diameter of 3 times 10 to the negative 8th centimeters, which is put in scientific notation. And one gold atom weighs something close to 3.3 times 10 to the negative 22nd grams. If you were to make a dollar bill out of gold, how many atoms would that take and how much would that weigh? So we'll look at that. Average dollar bill is about 6.6 centimeters by 15.7 centimeters and by about 1/100th of a centimeter thick. It weighs about 1 gram. So let's take a quick look at that now. Using our facts about gold, we're going to do some quick math for the almighty dollar. Figure out how much gold would be in that. So, based on what we've written down, that this is the dimensions of a dollar. And gold is about 3 times 10 to the negative eighth centimeters and weighs about 3.3 times 10 to the negative 22nd grams. A dollar weighs about 1 gram. So the math is, if that's centimeters per one atom, starting with that, 15.7 centimeters. How many gold atoms could fit across the dollar bill? 3 times 10 to the negative eighth centimeters in one atom. If you do that, type that in, 15.7 divided by 3 times 10 to the power of negative 8. It's going to be something like 523,333,333 atoms. Now, how many rows would be stacked end to end that would fit the height of a dollar? So 6.6 centimeters. Same math, because we're treating gold like a sphere with this diameter. So 6.6 divided by, in parentheses, 3 times 10 to the negative eighth power. Oops. That's going to be something like 220 million. So 220 million rows. And then finally, because we have to consider the thickness of this dollar, so 0.0109. Now, if you look in the book, they actually forgot to consider the thickness. They just assumed, oh, yeah, we're only going to have one molecule thin gold, but our dollar bill is actually much thicker than that. It's several molecules thick. 0109 divided by our 3 times 10 negative 8. And it's, how thick is it? It's actually 363,333 atoms thick. So that's quite thick. So how many atoms total would that be? So I'd multiply my 3 numbers together to get how many atoms. You can already see this is a very big number. So we have to, in turn, this is why we end up using scientific notation more times than not. Otherwise, we're dealing with really big numbers. So how many atoms? We use something like 4.18317 times 10 to 22nd. I'm going to just round this for now, but that's atoms. And now if each atom weighs something like, and one atom weighs something like 3.3 times 10 to the negative 22nd grams, how much would that golden dollar bill weigh? 3 times 10 root negative 22nd. A dollar bill would weigh something like 13.8 grams. 13.8 grams. There. So actually much heavier than a dollar bill. So that's just a little quick math. But each atom is a little bit different than the next. While a gold atom, using the gold atom as our standard, we compare that to a helium atom. A helium atom is about, we'll say, about half its size, yet it's about 1/50th of its weight. But if you look at a cesium atom is about twice the size of a gold atom, but only 2/3 of its weight. So each atom has different properties, and and they also are in largely different abundances in the world. Looking at this infographic from the book, we can see that in our universe, in our universe, 182 out of 200 atoms are hydrogen atoms. Nearly 18 of the atoms are helium atoms, and less than half of one of the 200 atoms are every other available atom. So hydrogen and helium are of the largest abundance, and of course, those are the key components that make our stars burn. Now, within the human body, over in the same 200 atoms, 126 of those 200 atoms are hydrogen. About another 51 are oxygen, another 19 are carbon, 3 of them are nitrogen, and one atom of those are everything else. Our calcium, our iron, our zinc, our copper, everything. So as we look at these atoms, we need to be able to classify these. The main way we'll classify them is with mass and weight, which will essentially be used interchangeably. Now, mass is defined as as the a body's resistance to acceleration. That's how we usually observe this. How far, how much do you have to push something against friction to make it move? However, looking at this, it can also be just a measure of the quantity of a matter present within an atom. Now, weight is the result of the pull of gravity on mass. So, most of our science will be thought of from the Earth's surface, so they will be essentially the same. However, if you try to measure your weight on the moon, it would weigh significantly less. Yet the amount of matter contained within is the same. In outer space, where there is almost no gravity, the your mass would still be the same, but your weight would be essentially zero. Now, these atoms were not truly indivisible. They could be broken apart, and when you break them apart, you can break them apart into basically the nucleus and the outer shell, as we see their example of a proton atom, a atom of hydrogen. Now, the nucleus is generally the positively charged central core of the atom. And in that positively charged core, you will always contain protons. Now, the proton is a subatomic particle with a mass of approximately 1 AMU and a charge of positive 1. Now, in all the atoms except for protium, which is the simplest form of hydrogen, the most common form of hydrogen, all except for in protium, most nucleuses will always also contain a neutron, which is a subatomic particle with the mass of approximately 1 AMU and no electrical charge. It would be neutral. Now, outside the nucleus and the electronic shell, we have electrons. We talked about them last chapter, but electron is a subatomic particle with negligible mass and a charge of -1. Now, one way to measure these guys are with the atomic mass unit, as you see. 1/12, the atomic mass unit is 1/12 of the mass of the most common type of carbon atom. So one carbon atom weighs 12 AMU. However, because we need to scale this up to the large scale. Because if you look at the mass of a proton, it's approximately 1.673 times 10 to the -24th grams. But we're going to just say, by turning that into AMU, it's 1.007 AMU. A neutron is 1.675 times 10 to the -24th grams. In AMU, that's 1.009. Both of those kind of round to approximately 1. And electrons, well, those would be 0.0009 times 10 to the negative 24th grams, which turned into AMU is 0.0005 AMU, which essentially rounds to 0. We can say that rounds down. So when we consider the mass of the atom, typically we only need to consider the protons and the neutrons. Now, in every atom, every standard atom, you will have equal amounts of protons and electrons. One proton with a positive one charge, with one electron, a negative one charge in this sphere and outside spherical shell, making the overall atom to be neutral, no net charge. Now, as we look at this, we can determine certain things about that atom. We can start to measure the mass number. Now, the mass number is simply the sum of the protons and the neutrons. So we care only about the protons and the neutrons when we consider its mass. But however, we will also need the atomic number, which is the sum of the atom, all of the atom's protons. Now, this atomic number is actually more important than the mass number, as that the atomic number is the key defining feature of any given element. Which element, of course, is defined as a substance whose atoms all have the same atomic number. So if I look at gold, every atom of gold will have 79 protons. Regardless of how many neutrons they have, they will all have 79 protons. If you lose a proton, it will no longer be gold. It will be changed into something else. And one thing to note is there is a possibility of an isotope. An isotope is an atom of the same element with a different mass number. Now, the most common isotopes we can talk about are deuterium and tritium, which are the isotopes of hydrogen. The most common form of hydrogen is protium, but we often just call it as hydrogen, where it has one proton, one electron, and no neutrons. But we can also get a deuterium, which is often seen in heavy water, and it's used in the function of the hydrogen bomb. Now, these are rather rare. They have one proton and one neutron, making the mass number 2, but it still only has one proton. Now, for every one deuterium, there's 6,700 protiums. So you can see deuterium is rather rare. Tritium, with its one proton and two neutrons, is even more rare, which we don't even really have a good fractional amount that can help establish how rare they are to at least naturally occurring. But we will form them in the process of making the hydrogen bomb. So they can be formed, and they are formed in various nuclear fusion reactions, but they don't naturally occur very often. Now, before we go any further, let's spend a couple minutes working through some ways of measuring our mass number, atomic number, determining our proton and neutron count. Let's see this in practice. Let's go ahead and work through some of these. We'll do some quick atomic number and atomic level math here. So when we write an element, we write it with the elemental symbol. We write the atomic number up top and the mass, or the mass number at top and the atomic number at the bottom. This number is intrinsically related to what element it is. So hydrogen or protium would just be 1, 1. Deuterium would be hydrogen 1, 2. And tritium would be hydrogen 1, 3. Protium meaning 1, deuterium meaning 2, tritium meaning 3. To figure out the proton and neutron count, this number is always related to the protons. So proton, all these is going to be 1. But the neutron count is going to be your atomic number minus your proton count. So 1 minus 1 is 0. 2 minus 1 is 1. 3 minus 1 is 2. So we can easily figure out how many neutrons by looking at that. So let's try some a little bit more complicated ones. So let's see. Boron, we'll say that's 511. So proton count. Proton is just going to be 5. Neutron, it has to be 11 minus 5. So it has to be 6. 6 neutrons, 5 protons. That's just the nature of how it works. Now, a lot of these elements, a lot of these early elements, will have close to equal amounts of protons and neutrons. But as we get into heavier elements, they will really start to diverge. So chlorine is going to be like element 17, it could be 35. So the proton count of chlorine would be 17. The neutron count would be 35 minus 17. 35 minus 17 should be what? 18. Let's look back at our friend gold. Gold is something like what? I'd like to say 79 and 197. So look at that proton count. Proton count's just 79. Easy as that. But neutron count, so we have to take 197 minus 79. Of course, having a calculator handy makes this really easy. So how many neutrons? It has 118. So it's getting really heavy at that point. A lot of particles. Let's look at maybe a few more. Look at a little bit lighter one, something like iron. Iron is something like 26 and 56. So proton count, 26. Neutron count would be 56 minus 26. Something like 30. Look at bromine. Something like 79 and 35. The atomic number of 35. So proton count, 35. Neutron count, 79 minus 35. So how many neutrons? Something like 44. One more. We'll just do a really heavy element like lead. Lead is 82, 207. 82. So proton count is 82. Neutron count is 207 minus 82. I know there's a typo on my calculator. I gotta fix that real quick. So 125. So that is how we can calculate the neutron count by looking at the mass number. Of course, you could plug these back in to solve your mass number if you're given a neutron count. Now, as we look at hydrogen, we would describe hydrogen having one proton in the nucleus and one electron in the outer shell. As we add a proton, we must also add an electron. And as we add the electron, that would make the element, as we add the proton and electron, would make the element helium. Now, the helium would have a filled quantum shell. Each quantum shell is the electron shell that surrounds the atomic nucleus. Now, it's possible to have more than one quantum shell, and each one will surround the previous quantum shell, building outwards. Now, the first quantum shell can only hold 2 electrons. Now, as we add, most heliums will have 2 protons and 2 neutrons, making a total mass number 4, but it will need 2 electrons. If we add another proton and another electron, we'll make lithium. But since the current quantum shell is full, we will have to add to the next quantum shell. And from there, we can kind of look at the electronic structure, which is the distribution of the electrons within the quantum shell. Now, this second quantum shell and in fact, the third quantum shell can each hold a total of 8 electrons. So as we add our way up to get to neon, we're going to keep adding 1 proton and 1 to the nucleus and 1 electron to the outermost shell. Once we filled up the second shell at neon and started the next row, sodium, we're going to fill in 1 electron at a time to the third shell until we get to argon. As we go into potassium, we'll add into the fourth shell, and the potassium actually holds, that row will actually hold 18 electrons. As it gets bigger, the shell can hold more electrons. So we'll look at that and look how that works. We look at hydrogen. Hydrogen would have its 1 proton in the center and be surrounded by a shell of 1 electron. Helium would have 2 protons in the center, have a shell of 2 electrons. Moving down to lithium, lithium would have its 3 protons in the center, core of 2 electrons, and a second quantum shell of 1 electron. Moving our way across to beryllium, would have 4 protons in its core, its nucleus, 2 electrons in the inner shell, and 2 electrons in the outer shell. We looked at boron, would have 5 protons in the core, 2 in the innermost shell, and it would have 3 electrons in the outermost shell. And this would keep going as we worked our way across until eventually on neon, skip straight to neon, would have our 10 protons in the core, 2 electrons in the inner shell, and 8 electrons in the outermost shell. And of course, the next row would be adding another shell around that as we go. Now, before we finish up, before we get onto the next chapter that looks at how compounds are formed when we combine elements together, we'll look at how the first 10 elements actually differ. So a little bit of history. Now, look at hydrogen. Hydrogen is Greek for the begetter of water. So the former of hydros, water. So this was originally discovered in 1766 by Henry Cavendish in the upper left. Later named by Antoine Lavoisier, who was later executed during the French Revolution. He was a scientist who funded his scientist/aristocrat, which back in the day you really had to be an aristocrat you had to be rich to kind of self-fund all these silly experiments you're doing, because there was not really a whole lot of people paying for science to be done. So you kind of be like, I'm rich, I'm bored, what should I do? I guess I should make things explode, try things out, mix things around. And so he was, among other things, a tax collector. So not very popular. Now, hydrogen, among other things, being lighter than air, also burns in air. And when it burns in air, it forms water. Thus, the name hydrogen. Of course, deuterium wasn't discovered much later, till 1931 by Harold C. Urey, which he eventually won the Nobel Prize of Science for that discovery. Now, moving along to helium. Helium is Greek helios for the sun. It was actually discovered in 1868, much later by J. Norman Lockyer. Now, this one is a quite unique discovery because while it's present on Earth, it wasn't really discovered on Earth till much later, because it was first noticed as you're looking at the sun to see what elements are in the sun, and just look at the different types of light that's coming from the sun. They found hydrogen, of course, but they also found a new light, which was our helium. Helium burning in the sun is emanating different wavelengths of light, and so that's why it gets the name Helios. Now, helium is much, much different than hydrogen. Hydrogen, responsible for the Hindenburg disaster, or the explosion of the great dirigible. Helium, completely non-flammable, which we now use for a lot of our purposes of hot air of blimps and whatnot, in that it's not reactive, but it's still incredibly lighter than air. And so we can use that, and if we pop a leak, a spark isn't going to set the whole thing off. Now, lithium and beryllium were both isolated from various minerals. Lithium was Greek for lithos, which literally means stone, because it was originally isolated in 1818 from a mineral petalite. Now, lithium is highly reactive. When you mix it with water, it forms hydrogen gas. We use this in batteries. We use this lithium carbonate as a mood stabilizer. You hear about people with manic depressive tendencies. They want to take lithium. Well, lithium is a highly reactive metal. Now, relatively safe to take. Beryllium was named after the mineral beryl, where it was most commonly found. It was found in 1797, a little bit before lithium. Now, it's in many precious stones, including aquamarine, red beryl, and emerald, which are beryllium-containing crystals. It's hard, it's toxic, it's often used to harden copper tools. It's used in things regarding like X-ray tubes. It's used in specialized components in the spacecraft and nuclear reactors. It's a very useful thing. We have boron, which was originally named after the mineral borax, where it could be found. This was isolated in its crude form in 1808 by Sir Humphrey Davy and discovered by Joseph Louis Gay-Lussac and Louis-Jacques Thénard. But it was isolated in a crude form, but it wasn't isolated in the pure form till like almost 100 years later. Now, boron is semi-metallic, which means it looks like a metal, but it doesn't act like a metal. Silicon is another semi-metallic thing, and we all know what silicon can do. We know that computer chips and all that it conducts electricity very well, but it does a lot of things that metals do not. Now, boron, not particularly useful in the pure elemental form, but it's very useful in various forms as a compound. We commonly see it in the antiseptic boric acid, which is also used as an ant killer, among other things. But borax, the super cleaning solution, is also using boron. Now, carbon, which was Latin for carbos, which is coal or charcoal. Now, carbon is our first non-metal. It's a solid. Is found in almost every compound relating to life except for water. It's known since prehistoric time. There's 4 distinct forms here that we can have. Charcoal, which is simply you burn something that contained carbon, whether it's living or dead, you make some sort of charcoal. You make that from trees, you get that from the grotesque pressures under the earth, kind of like put things into coal. But we can have graphite. Graphite is a slippery, solid form that is used as a solid lubricant. You ever slip that in to help your key turn in the lock? But it's also our pencil lead. So graphite, pretty common, pretty safe, pretty cheap. Diamond, of course, we all know diamond. It's a precious gem. It's incredibly hard. They use things, you need things like diamond cutters and like diamond tip drills, really hard. You can make into a really sharp thing. And of course, here's a type that you probably aren't familiar with. It's a Fluorine, more commonly referred to as a Buckminster Fluorine. But this wasn't discovered till 1985. So relatively recently. Now, this is a C60 molecule. It's made up of 5 and 6 membered rings, all interconnected. It looks like a giant soccer ball. If you've ever been to Disney World and you've seen the Epcot Center, that is modeled after Buckminster fullerene. And right now, there's still a lot of research being done with fullerenes and their properties and how to modify them and do lots of neat stuff with these guys. So there's still a lot of science out there to be done. Moving on to nitrogen, named after nitra, which is essentially saltpeter, the potassium nitrate that we use in gunpowder. Now, nitrogen was originally isolated in the 1770s by Joseph Black and Joseph Priestley, and separately by Carl Wilhelm Scheele. And a lot of the science is being done at the same time, and because we didn't have the internet, there wasn't a way to confirm and see what all people were doing. And so sometimes you get multiple papers on the same subject within a little period of time. And eventually we go, oh, he discovered it first because he published first. But a lot of people are trying to undercut each other and be the first to publish. Now, nitrogen, we know there's lots of medication with nitrogen. Ammonia, fertilizer, has a lot of nitrogen in it. A lot of nitrogen used in vitamins. All of our proteins, our amino acids. Amino means essentially nitrogen-containing acid. Now, oxygen, which Greek for oxygenes, which is literally begetter of sharp or begetter of acid. It was isolated in 1770 once again by Priestley and separately by Scheele around the same time. They were finding a lot of different gases all about the same time. Now, oxygen is in just about everything. A large variety of compounds, any proteins, carbohydrates, fats, oils, just about anything will react with oxygen. Now, fluorine is named for the various minerals it comes from. Fluorite, the fluorites. It was first recognized in the early 1800s, but we weren't able to isolate it till 1886 by Henry Moissan. That's because it's so highly reactive, you can't really get it pure elemental form, because if you make it and it reacts with something, then you don't got it no more. Now, it's used, it reacts with glass. So you're looking at like, oh, you make it, if you're storing it in glass, it's going to start reacting with the glass. It's kind of a little dangerous. We use it in the safer form as a fluoride to help harden our enamel. We use it in the non-stick coating pans, Teflon. It has like fluorines on the end of the groups, so it doesn't break off, and so things can't stick. It's used in chlorofluorocarbons, so that's used in refrigerants and aerosol spray cans. At least they used to be. Not so much, because they're a little bit dangerous for the environment, can break down the ozone layer. And of course, the last element, neon, which is Greek for new, was discovered in 1898 by William Ramsay, and not a whole lot of uses for neon, mainly used in neon signs. But it's a noble gas, much like helium, in that it's largely unreactive. So, now I'm going to leave you with a little bit of a writing prompt real quick. So, a writing prompt is look at one of the available elements that we didn't cover. Write a short little summary all about the element. Say when it was discovered, maybe who discovered it, where it was found, what are some of it, where it's used most often, common uses, a little bit of history. Just a short little thing that you can share with the rest of the class. Put it up on a discussion board. It's going to be first come, first serve. So I don't want a dozen uraniums, or so I'm going to give a list of people, and we're going to choose which one they want. Now, you can use Wikipedia, but I'd like you to use at least one other source as you work your way through that, and cite your source. If you're gonna use that one, paraphrase and cite, and have a little bit of a, well, It'd be nice if you could have a bibliography with that, but with a discussion board post or something like that, it doesn't have to be properly cited. If you're going to quote, don't just plagiarize. So needs to be at least 150 words, something like that. And then if you need to use more, I mean, you can go into more of the background if you need to fill up that space. Okay, that's where I'm going to leave you to. Uh-oh.